Welcome, everyone, to today's deep dive. We are really glad you could join us. So, to start us off, I want you to imagine you are hosting a party.
Oh, okay. I like where this is going.
Right. But it's not just like a big party. I want you to imagine a massive gathering with 80 billion guests.
Wow. That is a logistical nightmare.
It really is. And as the host, your job is basically to figure out the social dynamics of this entire room. You really have two main tasks. First, when two separate friend groups start to mingle, you need to officially introduce them and like merge them into one giant circle. That is what we call the union operation.
Okay, makes sense. Union.
Right. And second, you need to be able to point at any two random people in this absolute sea of 80 billion guests and instantly determine if they belong to the same extended social network. And that one is the find operation.
Yeah, and I mean, tracking those relationships among like 10 people is effortless, but what you were describing with 80 billion people is formally known in computer science as the incremental dynamic connectivity problem.
It's quite a mouthful.
It is. And when you scale that problem up to billions of data points, whether those are, intersecting roads on a digital map or millions of pixels in a high resolution image, the computational power required to keep track of who is connected to whom usually just skyrockets.
Which brings us to the actual focus of today's deep dive.
Yeah.
We have this stack of incredibly dense but really fascinating sources in front of us today.
Yes, we do.
There's a comprehensive Algo Academy guide, some really deep in the weeds engineering presentation slides, and a super recent research paper from KDDI. Together, they outline this data structure called Union Find. Some people also call it a disjoint set.
Right.
And the reason we are exploring this today, the mission for this deep dive, is because of this massive paradox at the heart of it.
Yeah, the paradox being that Union Find reached a state of, well, theoretical mathematical perfection decades ago. I mean, the math is basically solved, yet it remains one of the most fiercely contested battlegrounds in modern hardware engineering.
Exactly. And I want to focus on that phrase, first, mathematical perfection, because the time complexity of this algorithm is bounded by something called the inverse Ackermann function.
Which is just a legendary piece of math.
It really is. In Big O notation, which for those of you listening is basically how computer scientists measure how much longer a task takes as the pile of work gets bigger. This algorithm's growth is like almost non-existent.
Yeah, the inverse Ackermann function, which we denote as alpha n, is famously slow growing. For all intents and purposes in our physical universe, it is a constant. It just doesn't grow.
And the engineering slides we looked at lay out just how mind-bending that actually is. Because if your number of data points, your n, is 2 to the power of 65,536.
Which is an unfathomable number.
Completely. A number so large that the amount of atoms in the observable universe is basically zero by comparison. Even if you have that many data points, the result of this function never exceeds 4.
It's incredible.
4. No matter how massive the data set gets, the algorithm solves the problem in practically constant time.
It really is a stunning achievement in computer science history. So I think we need to look at how this data structure actually works under the hood, how some brilliant heuristics in the 1970s achieved that mathematical bound.
Right.
And then we can explore that core paradox, why modern software engineers are intentionally breaking that perfect math just to satisfy the physical laws of electricity.
Yes, absolutely. But let's start with the math. How does Union Find actually track all 80 billion guests at our hypothetical party?
So the core mechanism relies on building trees to represent sets of data. Imagine a classic top-down hierarchy.
Okay.
Every node in the tree points upward to a parent, and at the very top is a single root node. That root node is the representative for the entire group.
Like the founder of the friend group.
Exactly. So if you want to find which set a person belongs to, you just follow their parent pointers all the way up the chain until you hit the root. And if you want to union two separate groups together, you simply take the root of one tree and make it point to the root of the other.
But there's a pretty glaring flaw with that naive approach, right?
Yeah.
Because if you just carelessly link trees together without a plan, they can degrade into these long, stringy linked lists.
Yes, they absolutely can.
Going back to our party, it's like asking a guest who the founder of their social group is. And they point to a guy who points to a girl who points to another guy. And suddenly you have a single file line of 50 people you have to interrogate just to find the original founder.
Right. And in terms of time complexity, that degrades to linear time. So if you have deemed people, it might take n steps to find the answer. The data structure becomes incredibly slow as it scales.
Which defeats the whole purpose.
Exactly. To prevent this, computer scientists developed two brilliant strategies known as the twin heuristics of tree flattening. The first is called union by rank.
Okay, how does that work?
Well, when you merge two trees, you don't just do it arbitrarily. You evaluate the height of both trees first, and you always, without fail, attach the shorter tree beneath the root of the taller tree.
Oh, okay. That makes intuitive sense. You're basically ensuring that the overall depth of the combined tree grows as slowly as physically possible.
Exactly. But the real magic, the thing that gives us that inverse Ackermann bound, lies in the second heuristic, path compression.
Path compression. Okay, I love this one.
It's so elegant. This happens during the find operation. Every single time you travel up the tree to find the root, you don't just find the answer and walk away.
Right.
You take every single node you traversed along that path and you rewire them to point directly to the root.
Yes, I love this concept so much. It's like reorganizing a corporate ladder on the fly.
That's a great way to put it.
Right. You have this massive bureaucracy, and every time you have to ask a middle manager who the CEO is, you don't just say thanks and leave. You permanently pick up that middle manager's desk and move it right outside the CEO's office.
Yes.
So the next time anyone asks them, the answer is immediate. The act of querying the data inherently makes future queries faster.
It creates a perfectly self-optimizing system.
But here is where I always get tripped up, honestly. Reorganizing those desks takes work. Rewiring a data structure requires actual computing power.
It does.
How does the act of constantly changing the tree not cancel out the time you save? Like, how do they prove that these two heuristics combined yield that magical near constant inverse Ackermann bound?
Okay. To understand that, we have to look at Robert Tarjan's famous forest slicing proof from 1975.
Okay, taking us back to the 70s.
Right. Tarjan approached this by assigning a potential function to each node in the tree. Think of this mathematical potential like an electrical charge in a battery.
Okay, a battery, I'm with you.
He defined the potential of a node as the square root of its size. And size, in this specific context, means the total number of descendants reporting up to that specific node.
Oh, I see. Okay, so a node way up high in a massive stringy tree has a huge number of descendants. Its battery is fully charged, it's highly unstable.
Exactly.
But a leaf at the very bottom of the tree has 0 descendants, so its battery is basically empty.
Precisely. Now, when you perform a find operation with path compression, you take a node from deep in the tree and snap it directly to the root. By doing so, it gets stripped of its previous descendants.
Oh, right, because they got moved too.
Exactly. Its size shrinks drastically. Therefore, its mathematical potential, its battery charge, just plummets.
Wow.
Tarjan proved that the energy released from discharging that mathematical battery perfectly covers the computational cost of updating the pointer.
That is wild. The math essentially pays for itself.
It does. And because the trees are built using that first heuristic, union by rank, a node's size can only shrink geometrically so many times before it hits 0. Through this forest slicing logic, Tarjan definitively proved the upper bound of the algorithm. The math was completely airtight.
Okay, which brings me to my major point of confusion today.
Let's hear it.
If Tarjan solved this in 1975, and we achieved near constant time operations, even for like universes worth of data, aren't we done?
You'd think so, right?
Yeah. We planted the flag. The mountain is conquered. Why is there a comprehensive Algocademy guide, a modern slide deck, and a cutting-edge KDDI research paper all dedicated to optimizing an algorithm that is already mathematically perfect?
Because mathematical perfection on a whiteboard does not translate to physical perfection on a silicon chip.
Oh, okay.
There is a really specific slide in our sources titled The Grand Unified Theory of Union Find.
Yes, I remember that one.
It argues that in modern dynamic connectivity, algorithmic big O notation has been effectively solved. We aren't trying to do fewer operations on paper anymore. We are trying to do cheaper operations in physical hardware.
Because we've hit the physical limitations of how computers are actually built.
Exactly. We are hitting the walls of reality.
So we are basically leaving the realm of theoretical math and entering the reality of electricity and memory. Let's talk about the phrase those slides use for this: hardware sympathy.
Hardware sympathy is such a great term. It's the practice of designing software that works in harmony with the physical quirks of the machine running it. A perfect example of this is the multi-core contention bottleneck.
Okay, break that down.
Modern CPUs have multiple cores, meaning they process dozens of instruction threads simultaneously. If two separate threads are exploring our massive party, And they both try to union two overlapping friend groups at the exact same millisecond.
They could try to update the exact same memory address at once.
Right. And then data gets corrupted. The system crashes.
So to prevent that, classic concurrent disjoint set structures use something called a CAS, right?
Okay.
Compare and swap.
Yes, a CAS lock. It safely freezes a piece of memory, checks it, performs the merge, and then unlocks it. It guarantees absolute mathematical safety.
Okay.
But empirical benchmarking reveals a really stunning reality. According to the presentation data, when running these algorithms on real-world graphs, fewer than 0.002% of CAS operations actually fail due to a thread collision.
Oh, wow. Okay, so using a CAS lock is like installing a massive 2-ton steel bank vault door on your kitchen refrigerator. Just because you are terrified, your roommate might reach for the same milk jug at the exact same millisecond.
That's a hilarious visualization, but yes,
The
exactly.
real bottleneck to getting a snack isn't the threat of your roommate. The bottleneck is the sheer physical energy and time you burn constantly spinning that heavy vault wheel every single time you want a glass of milk.
And the kicker is, spinning that heavy vault door actively drains CPU power. The true enemy isn't logical concurrency, it's the hardware synchronization cost. Those locks trigger memory barriers that literally stall the entire processor.
So how do engineers fix it?
Well, engineers designing for hardware sympathy invented something called the plane right hack.
The plane right hack. So they just take the vault door completely off the hinges.
They do. Since collisions almost never happen, engineers just abandon the lock entirely and execute a standard unprotected memory write. But wait, what happens when that 0.002% collision actually occurs? Doesn't the whole system just crash, like we said?
It breaks the theoretical safety of the algorithm, certainly. But because of the redundant, self-healing nature of these tree structures, a collision doesn't actually cause a crash.
Really?
Yeah, it just results in a temporarily suboptimal tree path that gets flattened out during the next operation anyway.
Oh, that's brilliant.
By intentionally breaking the math and bypassing the lock, they yield up to a 40% physical speedup.
That is wild. They actively sacrifice mathematical certainty to make the physical electricity move faster.
Exactly.
But hardware sympathy doesn't just stop at locks. And this is the part that really surprised me when I was reading. According to the guides, modern engineers are actively abandoning path compression.
They are.
But why would we abandon the very thing Tarjan proved gives us the inverse Ackermann bound? I mean, we just talked about how brilliant it is. It all comes down to the CPU cache. Think of the L3 cache like a tiny, blazing fast scratch pad located right next to the processor core.
Okay.
Main memory, on the other hand, is like a massive filing cabinet down the hall. Now, path compression requires two distinct trips to memory. First, you traverse all the way up the tree to find the route that's reading the data.
Right.
Then you traverse all the way back down the exact same path to update every single node's pointer that's writing the data.
So you read up and then you write down 2 passes.
2 passes. And modern processors absolutely hate waiting. By the time your algorithm starts its second trip down to rewrite those pointers, the first nodes you touched might have already been erased from that tiny L3 scratch pad to make room for other data.
Oh, wow.
That is called a cache miss. When a cache miss happens, the CPU physically halts and waits hundreds of cycles just to fetch that data from the filing cabinet down the hall.
So even though path compression is mathematically optimal on paper, it creates a physical traffic jam in the actual silicon.
Exactly.
So what is the alternative then?
Yeah. Engineers pivot to path compaction strategies, specifically something called path halving. Instead of doing a full compression, path halving simply looks at a node, checks who its grandparent is, updates the pointer to the grandparent, and then moves up the tree.
So you just skip every other node on the way up.
Right. The brilliance of path halving is that it only requires a single interleaved pass. You read, you update, you move on. You never have to backtrack down the tree.
Oh, I see.
Mathematically, it leaves you with a slightly taller tree than full path compression. But physically, because it minimizes cache misses and drastically reduces memory transfer costs, it massively outperforms compression in real-world multi-core environments.
It's amazing. The physical architecture of the processor is literally dictating the math.
It really is.
But eventually, even with clever tricks like path halving,
Mm.
a multi-core CPU is going to hit a wall, right? If we want to process massive data sets, we have to look at the bottlenecks of the CPU itself.
Yes. A standard CPU has to deal with UNIFX non-uniform memory access, Essentially, if one core needs data from another core's local memory bank, it has to shout across the motherboard.
Which introduces massive delay.
Huge delay. When you need to process 16 million things at the exact same time, CPUs just choke. You have to move to the GPU, the graphics processing unit.
And a GPU is an entirely different beast. I mean, a high-end CPU might have like 32 brilliant, highly complex cores, but a GPU has thousands of relatively simple processing cores. It's like trading a dozen college professors for an army of 10,000 high school students.
That's a pretty good analogy. And because the architecture is so different, the bottlenecks change entirely. On a GPU, you distribute the work among thousands of what we call CUDA threads, which are just the individual workers executing instructions.
Okay.
But the enemies here are the overhead of launching those threads and the agonizingly slow transfer of data across the GPU's global memory.
Which brings us perfectly to the KDDI research paper, because they were trying to solve a real-world problem called Connected Components Labeling, or CCL.
Yes.
Let's visualize this for everyone listening. Say you have a black and white security camera feed of a highway at night. The cars are white blobs, the road is black. CCL is the computer vision algorithm that scans the image, finds a connected group of white pixels, and says, okay, this blob is car 1, this blob is car 2.
Right. And doing that in real time requires looking at millions of pixels and figuring out if the pixel next to it is part of the same object. It is fundamentally a massive union find problem.
Wow, okay.
The KDDI paper notes that CCL is used for everything from fast 3D shape measurement using blink dot projection to real-time multi-camera video analytics.
And the researchers at KDDI achieved something truly staggering here. They built an optimized parallel union find algorithm that hit up to a 5x speedup over conventional methods.
It's a huge leap.
They successfully labeled a massive 4096 by 4096 pixel image in just 3.36 milliseconds. That is over 16 million pixels categorized almost instantly. How did they pull that off?
They engineered a highly specific three-phase GPU local merge.
Okay, phase 1.
The first phase is coarse labeling. They divide that massive 4K image into smaller, bite-sized 2D blocks, and they assign each block to a cluster of CUD threads. But here is the critical design choice. Instead of having those threads constantly read and write to the GPU's painfully slow global memory, they load their specific block into their own localized shared memory.
Oh, that's smart. It's like taking a stack of files from the basement archives and bringing them up to your desk.
Yeah.
You do all the paperwork right there at your desk where it's fast, rather than walking down to the basement every 5 minutes.
Exactly. Once the data is in shared memory, they perform row-column unification scanning left and up to unify the pixel labels.
Makes sense.
Then comes phase 2, which is the absolute masterstroke of the paper, boundary analysis. In a naive parallel approach, you might try to run union find on every single pixel across the entire image to connect the separate blocks together.
But KDI realized that the interior pixels of those little blocks are already solved by phase 1.
Exactly. So they entirely ignore the insides of the squares. They only perform union find on the specific cells that straddle the boundary line between two thread blocks.
Oh, wow.
By only checking the scenes between the blocks, they drastically reduce the number of CUDA threads they actually have to launch. They minimize the computation to just the edges.
That is so elegant.
And finally, in phase 3, the global link, these stitched together boundaries are merged into a single final topological map representing the entire image.
It is just the ultimate manifestation of hardware sympathy. They rewrote the algorithm not because the core math was wrong, but to avoid the microscopic physical distance that electricity has to travel between the GPU's global memory and its individual cores. They localized the math so the electricity wouldn't have a long commute.
It illustrates beautifully how an algorithm is never truly complete. Software engineering is a constant, evolving negotiation between logical purity and physical constraint. The union find data structure isn't just an abstract academic puzzle, it is the invisible engine powering vital systems all around us.
Yeah, the Algo Academy guide lists so many of them. I mean, it's the engine behind Kruskal's algorithm, which computes the minimum spanning tree for physical road networks or internet topology. It finds the absolute cheapest way to connect cities with asphalt or fiber optic cables.
It is also foundational in percolation theory. Physicists and material scientists use union find to model how fluids flow through porous materials.
Oh, really?
Yeah, whether that's groundwater moving through soil, or engineers modeling oil extraction, and of course, clustering pixels for real-time computer vision like we just talked about.
It's literally everywhere. And looking at all these sources together leaves me with a final, somewhat provocative thought for you to ponder today.
Let's hear it.
For 50 years, computer scientists have obsessively optimized this disjoint set algorithm. We started with brilliant, unassailable math. Then we spent decades fighting the physical limits of silicon. We dodged cache misses, we tore down memory barriers, we intentionally broke locks. We meticulously molded the map to fit the physical constraints of a microchip.
Really did.
But computing is currently on the verge of radical foundational shifts. We are looking at a future with quantum computing, which operates on entirely different principles of probability and entanglement rather than binary electricity, or biological processors, utilizing lab-grown neurons that compute chemically rather than electronically.
It's a brave new world.
Right. So when the physical architecture of what we define as a computer fundamentally changes, what happens to our math? Will these perfectly engineered hardware-sympathetic algorithms seamlessly adapt to the quantum realm? Or will all of this incredible optimization be rendered entirely obsolete, forcing us to start back at square one?
That is a fascinating question.
Next time you host a massive party and you're trying to figure out who belongs to which friend group, take a moment to think about the invisible, mathematically near-perfect algorithms running silently in the background of your life, and the incredible logic-breaking lengths engineers go to in order to make them just a fraction of a millisecond faster. Thank you for joining us on this deep dive.